Should I start? Okay. Well, thank you for joining me. Today I will be giving a presentation on adjoint electric field conjugation, specifically for a vortex coronagraph. What? Oh, okay. And most of this work is for a paper that is in prep at the moment. So yeah. So basic introduction first. The question we want to be answering isn't actually, are we alone, given the statistics of how many stars are out there, how many planets orbit most stars. We can conclude that probably there is life out there, other than us. But the real question is, how alone are we? And to answer this, we have been designing coronagraphs and telescopes such that we can study nearby stars for exoplanets. And this on the right is an example of the type of image that we want to be able to generate one day. Specifically, this was a simulation done for the LUVOIR A, I think the Eclipse coronagraph, where they showed what a solar system analog might look like at, I think it was 10 parsecs or something like that. So yeah, we would be able to image something like Venus, Earth, and a big Jupiter way out from the center of the star. Coronagraphs can also help us study protoplanetary systems and in general just understand solar system dynamics and formation much better as well. Such as we can understand debris disks and their interactions with planets too. So that's the goal behind building telescopes and coronagraphs specifically.
You already passed your qual, but why 10 parsecs?
Well, I think 1 parsec is where it's one astronomical unit is 1 arcsecond or 1 arcminute. I forget which actually.
Probably second.
Arcsecond, yeah. So then, yeah, 10 parsecs. I think it's a good number to use.
That's basically it, and it does make the math easy.
Yeah.
Of separation.
Yeah.
There's also a bunch of stars between us. Like
Yeah. That's like the general number I hear when people refer to nearby stars. That's why I had it in quotes there. But yeah, the challenge with building coronagraphs is that stars are much brighter than the planets. So diffraction effects from the star actually end up obscuring the planets. So we designed the coronagraphs to block the star and mitigate its diffraction effects. And I put block in quotations here because some coronagraphs use a physical occulter, such as a focal plane mask, that's just a disk that blocks the on-axis starlight. But coronagraphs, such as vortex coronagraphs, do get more complex and they use diffraction effects to attenuate the starlight. So yeah. The problem is, even after we design these coronagraphs, whether they have some exotic shaped pupil mask or exotic focal plane masks and Leo stops, optical surface errors still end up producing what we call speckles in the image plane. And these are additional diffraction effects from surface errors, such as the example you see here, where you have some range of high order amplitude and optical path difference errors throughout your optical system, and these accumulate into these speckles at the final image plane. This term is not to be confused with laser speckle. Two different things in optics. It was an unfortunate naming accident, I think, that we ended up calling these speckles in our community. But at least that's what I've heard. So now we have to figure out how to deal with these speckles, and to do this, we use adaptive/active optics to correct for them. In doing so, we use deformable mirrors, which have a continuous phase sheet, and then we can poke a bunch of these actuators behind the mirrors in order to deform the phase sheet and control the light how we want. These deformable mirrors, typically you assume that each actuator has some sort of an influence function. And in our case, we usually just approximate this influence function as a Gaussian with some specified interactuator coupling. Again, in our case, we'll get into the DM we are using, but we assume a 15% coupling between actuator and actuator. That means if I poke one actuator up here, or I guess down, an amount of 1, then the nearest neighbor actuator, which would be here, would have an amplitude of 0.15. So that's what we mean by actuator coupling. And then this is something interesting. These deformable mirrors, we are modeling them as these continuous phase sheets, but they are not actually these continuous phase sheets. They are actually these very strange structures on the nanometer scale. These are measurements of a Boston Micromachines DM done for modeling HABEX back when that was still a project. And you can see there are these strange structures all throughout the DM surface. This is an actual depression in the DM, this little spot in the middle where the post behind one actuator is. And then these tiny things here, those are just holes used for the etching process of the DM. I think they're about like 2 microns or somewhere between 2 to 10 microns in diameter. I don't remember what John Christ quoted in his paper, but yeah. So moving on, how do we actually use these DMs to correct for the speckles? Well, the most common algorithm that's been implemented so far is electric field conjugation, and that does what it sounds like. We compute a Jacobian, which estimates the response of the electric field in the image plane for each actuator. We invert that Jacobian, and then we use that inverted Jacobian, which we call the control matrix, or the reconstructor, as it's called in some other contexts. And then compute the actuator commands that conjugate or destructively interfere the electric field in the image plane. This is a flow chart of what EFC actually looks like. First, you have one step, which is computing the Jacobian with the instrument model. And why we need an instrument model in the first place is because we can't directly measure electric field with our detectors. So that's why we do all of this with a model in the first place. And then once you have that Jacobian and your control matrix, you can then iteratively sense the electric field in the image plane, which requires a separate algorithm in and of itself, actually. Also model-based. We refer to this algorithm usually as pairwise probing, but there are different methods out there. And then you compute the actuator commands and rinse and repeat. But computing Jacobians is very annoying. It can take a long time, particularly with systems that have a lot of actuators. And for projects such as HABEX or now as it's called HWO, they're looking at 2 DMs with 96 by 96 actuators. That's going to be a lot. So computing those Jacobians takes a very long time, and there's also a very large memory requirement for those Jacobians. We'll get into one example of it in a little bit, but dealing with those large arrays can be cumbersome, and on radiation hardened processors, in some cases, absolutely not feasible. So as a possible solution, adjoint EFC, or you might also hear it as algorithmic differentiation EFC, was introduced to avoid Jacobians altogether. And this was actually demonstrated by Scott Will in 2023, where on the HiCAT testbed, where they were able to dig an annular dark hole from about 6 to 10 lambda over D and reached about 2 times 10 to the minus 8 contrast. So taking a step back again, actually, what does the forward model do? Well, the main input to the forward model is our desired DM command. And then that we propagate from the DM command to how we model the DM surface, and then apply that to the total pupil plane phase, propagate through the focal plane mask to get the LEO pupil phase and amplitude. I should just say wavefront, and then propagate from the LEO pupil down to the final image plane. In this case, I just applied a waffle pattern, which produces these speckles in these corners of our control region. So this is just an example of what we use the forward model to do. So now, how do we actually compute gradients of the actuators for EFC? Well, we start by defining a scalar cost function for EFC. This cost function has three main terms. EAB is going to be that's the electric field we actually measure in the image plane of our camera. Again, there's a separate algorithm required to do this measurement, but we assume for now we've measured it, we know what it is, and then we can move on to computing E, I call it del A. And this is going to represent the electric field that a new DM command produces, or I should say just a new actuator command produces in the final image plane. So we sum these two and then take the L2 norm of them. The final term is this L2 norm of del A times alpha. And this is just a regularization term that we use to make sure that our DM commands don't blow up. So we apply some constant to this to make sure the range of our beam stroke being used is being controlled as we want it to be. So yeah, how do we actually compute E del A? Well, this is where we use the model to do so. First, we compute E, or E nom actually is what we compute first, which is just we apply the knowledge we have of the current state of our system, which is going to be whatever measurements we have, however we're modeling the vortex or the focal plane mask, and the current actuator state for whatever control iteration we happen to be on. So we compute E nom. And then we compute EA, which is the new electric field plus the current state of the system plus the new desired DM command, which is del A. So yeah, and then just subtracting these two, you get E del A. Finally, we compute the gradient of the cost function J with respect to the actuator command E field. This has a separate derivation to it, but it turns out this equation just simplifies to 2 times EAB plus E del A. You can follow the algorithmic differentiation rules in order to derive this. This was done in Scott Will's paper, so I just used this equation. Then comes the very tedious part, which is we have this gradient. How do we actually propagate this all the way back to our DM actuators? And this is where we use algorithmic differentiation again to hand derive an adjoint model. That's at least what we're calling it here. And then so from this adjoint model, we propagate all the way from this row where we have our gradient back to the DM actuators. In this particular table, what I'm showing is all of the forward model operations required for a generic 2DM coronagraph system, as well as every adjoint operation in the adjoint model that is required for each forward model step. So together, we call these the control models of our system. But yeah, I made 2 simplifications in this table, which were where is it? Yeah, the forward DM operations and the forward vortex operations, as I'm calling them, as well as their respective adjoint DM operations and adjoint vortex operations. And so it's generally a good thing to divide things into submodules when you're programming them. So I divided these forward DM operations and forward vortex operations all into their individual submodules. Those equations are all here. So since equations are boring usually, here's what adjoint propagation actually looks like when it's visualized. We start with whatever the electric field is or the first gradient we computed was from our focal plane, propagate back to the Leo plane, then to the total pupil plane, and then to the surface of the DM, and finally to the actuators of the DM. So again, you can just follow the equations I previously presented step by step to make your way all the way back to these actuators. So does this derivation actually work? Well, coronagraphs are hard to come by, so running simulations are the easiest way to test. And the way we approached this was to make an independent Fresnel model of a vortex coronagraph. And so in these simulations, that Fresnel model acts as our truth. So the distinguishment here is between the Fresnel model and then again, the control models that we are using to compute the gradients. Here's an example of what the pre-FPM pupil amplitude and OPD looks like in the Fresnel model, followed by the normalized PSF and the mean contrast with our first coronagraphic image. So running a quick simulation, in this one, first we started with just a monochromatic simulation that includes pairwise probing. Again, pairwise probing is the algorithm used to actually estimate the electric field at each control iteration. And so we confirmed that, yes, the hand-derived adjoint model is working. We are computing the gradients correctly and digging a dark hole when the way we want to be with the Fresnel model. You can see it's actually pretty easy to reach 10 to the minus 10 contrasts in simulations with no noise. But things do end up getting a little bit more difficult in broadband. And so for these broadband simulations, we use 15 wavelengths to simulate an image in a 10% bandpass. And we simulate EFC as a baseline. In both the EFC and aEFC cases, we see convergence within 10 iterations to below 10 to the minus 10 contrast. So again, we're confirming that the aEFC algorithm is working as expected. And one note is that
Can I ask a quick question? Is that always, is the one-time trial is average, you get a curve?
What do you mean?
What's the prompt made by only one trial, it made by average of several try?
I'm confused.
I mean, it's a mean contrast, so how many iterations you do?
So this is 10 iterations of EFC and aEFC. Do you mean like how many iterations of the optimizer are used?
So you are doing the average of to make the curve, right?
It's the average of the contrast in the entire dark hole.
We define the average, we define the contrast as the mean contrast within our desired dark hole region.
It's not different trials. It's,
So just one try.
yes.
Yeah. So yeah, we what was I saying? Oh yeah, the note is for EFC and adjoint EFC, we were using 3 control wavelengths here to span the 10% bandpass. So there's a slight nuance there when you're computing the gradients. You actually compute the gradients for each control wavelength individually, and then you just sum them all up, and that's your final gradient. One note here is that we limited the optimizer for aEFC to 50 iterations, just because every now and then the optimizer can start to take a long time to converge. And so this is just a good way of saying, just stop after 50 iterations. I'm sure it's good enough by then. So yeah. Also, the EFC Jacobian, because we were using 3 wavelengths, 96 by 96 two 96 by 96 actuator DMs, the final Jacobian was massive. It was 23 gigabytes using 64-bit precision. So again, that motivates why when you're dealing with systems at this scale, aEFC becomes much more feasible than EFC. Yeah. What about dealing with model errors, though? Well, we only need the model to evaluate the gradients actually. We don't need the model to tell us absolute truth of the system. So at least in the case of algorithms such as EFC, we can still converge in the presence of model error. In this case, we were simulating model error with the DM1, DM2, and Leo stop lateral positions and just simulated a shear. So what if something gets misaligned while it's in orbit or as it's trying to get into orbit? So yeah, the thing is, it takes longer to converge because the gradients don't point in exactly the right way you want them to, because of the model error. So you can still converge, but it takes more iterations. And you also have to use this beta bumping technique, which is changing the regularization term every now and then in order to kick us out of a local minimum solution and then reconverge down to a better solution. So that's the point of beta bumping.
Can you learn to improve the model, or is what you're modeling changing so that you can't like use AI to learn and iteratively improve over time?
You can learn it. There are people working on a method to, let's say you compute one Jacobian to start with, and then you run 5 iterations of EFC. You use the electric field data from those 5 iterations, and then you run a separate system ID algorithm in order to figure out how the Jacobian needs to change such that it maximizes the probability that the electric field measurements you got are what the model produces. So yeah, people are working on system ID to do this, but it's complicated, to say the least. So if you can just have a good state of your system in the model, then it's easier to just use that. There's also additional factors such as, well, would system ID be feasible on radiation hardened computers? I don't know the real compute requirements behind that, but yeah. So finally, after doing a bunch of simulations, we turn to, does this actually work on a real instrument? And as it turns out, we have a coronagraph right here called Scoob, and it is perfect for testing aEFC. And then I say, well, maybe not perfect because it's actually very tedious to try to get the measurements you want and try to calibrate the instrument model to then actually deploy aEFC. But here's the general layout of the instrument. Here at the focal plane mask, this is where we have our vortex coronagraph. And right before this focal plane mask, we typically insert a fold mirror by hand and redirect the light to this, what we call the phase retrieval camera, in order to measure this pre-FPM pupil plane amplitude and OPD. And you may wonder why I've been specifying pre-FPM this entire time. It's just because the aberrations that are pre-focal plane mask are the most important in a coronagraph system. So that's why. So, yeah. And before actually doing an aEFC test, we did an iEFC test, which is similar to electric field conjugation, but it's a purely empirical method. So no instrument model, you compute a Jacobian, or you measure a Jacobian instead of computing one. And the disadvantage of iEFC is that it does require empirical calibration, which in low flux regimes can take a very long time. And again, this keeps coming up. It would take an even longer time for systems with a large number of actuators because there's a lot of modes you would have to calibrate or measure the response of. But anyway, at least on Scoob, aEFC has been the best performing algorithm up to date. So we use this to define our known best contrast. And with this, at least in monochromatic light, we're able to consistently get to around 2.5 times 10 to the minus 9 contrast within 30 iterations. And then with aEFC, we still converge, and it's converging down to below 10 to the minus 8 contrast. In this case, we got a best of 8.1 times 10 to the minus 9, which is not quite as good as the aEFC test, but it at least shows the adjoint model is working on real hardware. So the gradients through the vortex chronograph are being computed accurately. But the potential issues here are model errors related to the focal plane mask. Actuator gains is actually a big one. One of my suspicions is that the actuators in the model need to be like accounted for in terms of the gain that we actually see on Scoob. Subpixel image registration is also a big one. And as well as the influence function form. Like I said, I was just approximating the influence function as a Gaussian, but it's not really a Gaussian. It's actually, the real influence function isn't even perfectly rotationally symmetric. So all of these things can add up such that model errors do end up limiting you at some point. And these are things that you just have to measure on the test bed. We just haven't done that on Scoob yet.
How do the computational resources compare for the aEFC and the aEFC? Are you doing all this using like a neutralino computer board or?
No, we are just running everything on the GPU on our lab computer at the moment. So yeah. Also, the computational requirements on Scoob for standard EFC or aEFC aren't that bad because we only have 952 actuators. Not, I think the total was 14,000 actuators in the simulations up here with the 296 by 96 actuator DMs. So yeah, it scales by factor of 14 when you scale up to 2 DMs like that. Yeah. I do understand your point, though. We probably should
I'm really
be
wondering
testing.
whether this is
Yeah,
workable on the ESC
yeah.
with the computer resources.
That's one of the things we are working to benchmark and implement the algorithms on neutralino boards.
But you have to, right? Like if IEFC is doing better, you have to compute. Is there a reason to use AEFC?
Only if you are worried about drift in your system from when you calibrate aEFC to then actually digging the dark hole. Or trying to maintain the dark hole with aEFC.
Could we do the aEFC first and then turn to aEFC?
Probably you could try that.
Yeah, it depends, because you guys, then you don't have to calibrate it off, because the calibration with IEFC takes time, right?
Yeah.
Oh,
So if you can, maybe you can get down the ramp.
Yeah, if you can like start down here, that's best.
Exactly, yeah, and you
So,
can hack out.
Yeah.
Maybe there's a trade there that's not so much about getting the best contrast, but getting to the best contrast as quickly as possible.
yeah.
Because in some ways, like this modeling stuff, I mean, it's one of the reasons that EFC is like classic Amir.
Yeah.
EFC is like really hard, right? It's that the models.
Yeah, it's hard to calibrate the model.
Yeah, and they change underneath. At some level, eventually there's certain things you can apply, you can measure and apply, and then there's other things that are just changing underneath you.
Yeah.
But yeah, if I can help you get down that ramp real quick, that'd be a big win, I think.
Yeah, at least, I mean, in the case of what the Roman coronagraph is doing, I mean, they dug dark holes in TVAC before they are launching. So they're gonna start this algorithm in orbit with the dark hole command from TVAC.
Except they aren't. It's grounded in the loop.
Hmm?
It's grounded in the loop. All your dark hole digging is done on the ground.
Oh, yeah,
Yeah.
but you're still starting the
That's
dark hole state with the TVAC initial iteration or the TVAC final iteration. So I think they're probably gonna end up starting with like a contrast of, I don't know, 10⁻⁷ or maybe even below that. Because they were getting down to 10⁻⁸. Hmm?
I don't know, it's that good between the TVAC and then you launch and then there's a lot of things that have to work. Right?
Yeah,
They don't have a telescope in the TVAC. Right, they don't have.
Yes. At least in current TVAC.
Yeah.
So I imagine there's gonna be. That means they were assuming a different wavefront than what the wavefronts.
Yeah.
Stuff. Which means. Yeah, probably will start with something much higher.
yeah, I forgot that they didn't have M1 in TVAC.
Although I wouldn't be surprised if.
I mean, they had a telescope simulator.
Yeah.
They did, but I
Yeah.
wonder, it doesn't mean it's gonna have the same aberrations that
Yeah.
it cycles per diameter or whatever.
Okay, well, anyway, that was the final technical slide. Basically, we have demonstrated aEFC with a new hand-derived adjoint model for a vortex chronograph. And the simulations at least show that aEFC can converge to 10⁻⁻10 with relatively few optimizer iterations, which was the 50 optimizer iterations that I limited aEFC to. And then, yeah, Scoob performance is encouraging, given it's the first model-based demonstration on Scoob, but we need to put more time and effort into improving the model if we actually want to consider deploying an algorithm like this. So.
Yeah, I wonder how you evaluate. How much work you put into the model.
Yeah, I don't know.
Yeah. There's diminishing returns at some point.
Yeah.
So from what I understand, system ID is like you use empirical measurements to like sort of nudge your Jacobian in the right direction, right?
Yeah.
Is there like a similar sort of version of system ID that would work with like a forward and adjoint model that could like make slight nudges in your models and learn it over time with empirical data? I'm not sure if that's something that.
Yeah,
Scott has ever looked into.
I'm not actually sure you would even need an adjoint model to do system ID. With this, like say the parameters you are interested in figuring out are the lateral position of your Leo stop, the lateral position of DM1, DM2, then you take those electric field measurements you got, and then you would run some sort of optimizer on with your forward model to, like, I guess gradient descent your way down to figure out those parameters. It gets really tricky at some point because, I mean, you can just add more and more parameters, and the problem is the more parameters you add, the more unstable the optimizer becomes.
Yeah, because I assume there's probably going to be multiple things you can tweak that might give you sort of similar results. Yeah, there's a lot of degeneracy there.
Yeah.
Maybe there's some sort of diversity you can come up with, but I have no clue.
Yeah.
So what constraints do you have on the input conditions to make this all work? I mean, do you have anything on what level of wavefront you need coming in or stability of that wavefront or anything about speckle lifetimes or anything or?
Yeah, so as far as speckle lifetimes goes, we are, at least in the simulations we're doing here and on Scoob, the speckle lifetimes are on the order of like, or we assume they are going to be on the order of minutes. And what we see on Scoob is that they are on the order of like 10 minutes usually. We don't see that much drift in the speckles. So
You're cheating.
yeah, but we're cheating because we don't have real thermal gradients to deal with on Scoob or as far as the stability of the input wavefront, that's that's the problem for whoever is working on Lofus, which, yeah, I'm gonna leave it at that. Yeah.
Can we go to the first page of simulation?
This one?
No, this. So the question is just, I use. Why you have to use 64 bits? Because your contrast ratio is only 10 minus 11, right? So it made me thinking probably 16 bits is enough. And 32 would be pretty sufficient.
So we use 64-bit because that's the standard we use in scientific computing. I don't think 16-bit would be enough. 32-bit I have heard might be enough. I think the problem here is this is intensity, and electric field is going to be the square root of that, and it's complex. So these are actually, the simulation data is complex 128s.
I don't even think 32 is enough for anything below.
So 16 will give you accuracy about 10 minus 14.
In machine precision, yes. That doesn't quite translate to like when you're doing operations.
You have to care, yeah, you have to think about the domain diverge.
Yeah, but yeah, as far as why 64-bit, that's the standard in scientific computing. So
Because I
that's
think
what we are
you are
assuming.
trying to highlight the memory size you need. Probably when we go down to 32, then you can save up the memory.
Yeah, definitely going to 32 would help. But even a 11 gigabyte Jacobian is a lot for radiation hardened processors. It's not necessarily the memory capacity on those processors either, it's the memory bus. So how fast can you access the memory? That makes things tricky.
So what's the memory requirement for the aEFC?
Oh, we have not done that trade study yet. It's much smaller than 23 gigabytes, though. It's probably around like 1 gigabyte, because really the only things you're storing in memory are the arrays for the optical model. So like, what is your pupil?
96 multiplied by 96.
Those are the DMs. For the arrays, I use like a 1000 by 1000 pixel pupil.
Yeah.
So
1.5 gigabyte, I would say. But you have 3 colors.
Yes. So 3 control wavelengths, but you can use the same pupil data for each control wavelength. You just need to scale the OPD by lambda. So, or delta lambda. Yeah.
So on Scoop, how long does it take to run through your set of iterations?
Typically like 45 seconds-ish, around there. Yeah.
I was just wondering how it was going to compare to the time over which conditions are changing and whether you're constantly chasing or whether you can be, stable for a little while.
Yeah.
Scoop has a ridiculously bright source on it too.
Yes.
It's not the second or third magnitude.
No. Yeah, when I was saying the 45 seconds, though, that was like just computation time, not exposure time. The exposure time I was like, here, let me go to this.
Just wondering how fast things changing in the background.
Yeah, for when I was running pairwise probing or actually measuring these images for contrast, I typically do an exposure time of like 100 milliseconds. and stack 30 frames. So each exposure was 3 seconds each. Yeah.
It's my post.
Yep.